we move to the next presentation, which is an online one. Will be given by Jeremiah Scully, and the title is Mitigation of Radio Frequency Interference in Solar Radio Observations using Generative Adversarial Networks. So we see Jeremiah online already, and yes?
Can everyone hear and see me, can they?
Yes, we can hear and see you fine. So if you could put your presentation in presentation mode.
So, hi everyone.
Yeah, I'm going to give you a 5-minute warning, okay?
Perfect. Hi everyone, my name is Jeremiah Scully. I'm a PhD student in the Technological University of Shannon here in Ireland, and this is my research titled Mitigation Radio Frequency Interference in Solar Radio Solar Radio Observations using Generative Adversarial Networks. So RFI, what is it? So RFI stands for Radio Frequency Interference. It refers to essentially unwanted signals and noise that can be picked up by radio telescopes or other radio astronomy instruments. RFI can obscure and distort signals that radio astronomers are trying to detect from celestial objects. In other words, it's essentially kind of annoying. The purpose of this research kind of built off my previous research. You can see here on the right here, where we actually use YOLO to identify type 3 solar radio bursts. And you can see in this case in the test set that there is RFI here in this image, and it's actually causing the YOLO algorithm to go absolutely mad. So this kind of spawned this kind of research where we try to essentially can we actually teach AI to detect and mitigate the effects of RFI completely. So what causes RFI? So it can be caused by human-made sources. So we have examples here. So cell phones, Wi-Fi routers, microwave ovens, power lines, etc. We've natural sources, including lightning, solar flares, and cosmic rays. We've satellites. We typically those that transmit in the same frequency as radio telescopes. We have aircrafts, obviously flying overhead can cause RFI. And those are equipped with radar or other electronic systems. And then there's of course, astronomical objects such as the sun and other stars can cause RFI, particularly if they emit strong radio waves. There's actually a lot of research on current RFI mitigation methods, such as shielding, such as metallic shields, walls, roofs that block radio waves from entering the telescope. And then there's filtering, either by time or frequency. And there's obviously frequency management, which obviously goes under the category of filtering. And then there's signal processing as well, again, which that goes under the category of filtering in terms of time and frequency. A lot of RFI mitigation happens before actually the even telescope is constructed. Or a lot of radio telescopes are actually located in remote areas where there's actually no interference, no kind of signal contamination, if you will. And then there's been a lot of research as of late for artificial intelligence that come into play for RFI mitigation. But a lot of them actually just are kind of flagging methods where they actually detect RFI and then use the traditional signal processing and filtering algorithms to actually mitigate it. So this research is we're kind of exploring the area of can we detect, not only detect and learn, but also mitigate using RFI as well. So this is the telescope we're using for this research. It's the HELIOPHYSICS station located in Burghcastle here in Ireland. It contains 96 high-band antennas that operate between 110 and 240 megahertz. And then we have 96 low-band antennas operating from 10 to 90 megahertz. For this research, we actually just focus in on the low-band antennas because that's where it's kind of highly susceptible to a lot of RFI. These are the type of events that you associate at this frequency. So at the top right, we have a few type 3s, and then at the bottom right, there's actually a type 2, which we actually don't use in this research I just highlighted here. So the bottom we actually use in type 3s kind of observation. So this is where I introduced the actual algorithm itself. It's RFI removal generative adversarial network, and it's actually based on the GANs network itself. So I'm going to just introduce the GANs network first before I actually introduce the more complex network. So the GANs network is actually made up of two kind of small networks. We have the generator that simulates, in this case, it's type 3s from just pure random noise, random vectors, random numbers, and it upsamples to actually get a 128 by 128 image. And then we have the discriminator, that its job is essentially to actually distinguish between what's simulated and what's not. And then the loss is fed back into the generator, so it actually improves over time and get more believable simulated examples of type 3. So kind of bear this in mind, because the next network is kind of a bit more complicated than this. So when creating this network, what we wanted to do was we wanted to highlight an area, so being the RFI region, and essentially remove it. So we kind of looked at this kind of this network here. It's called the eyeglass removal GANs, or GANs for short. And what this does is essentially takes the generalist MeGlass data set, and it highlights a mask area of the glasses framework between the eyes. And using the generator, it actually simulates an eye region without glasses. So we kind of adopted this framework and converted it into a kind of an RFI GANs removal network. So the ER GANs, if you remember before, the generator and discriminator, the generator adopts a similar framework to an autoencoder, where we take actually 2 inputs for the generator rather than a single input. And we actually mask in this case, the organs case, we mask the region of the eye area, and we actually kind of generate from pure numbers, realistic, believable examples of the eye region. And then we feed these examples into the discriminator and compare glasses without glasses. And then this is again fed back into the generator. Now, in our case, what we do is we actually don't change the network at all. The network stays the same. The only change we actually make is the actual input itself, or the mask area. So we actually increase the mask area from the actual eye region to the whole image, essentially the whole size of the image. And again, the second thing we actually obviously change is the data set itself. So we have 2 training sets, one training set containing RFI and one without RFI. The 2 training sets are identical, exact same images, except one's containing RFI, one has no RFI. So the training sets, as I said, there's 2 of them, one with RFI and one with RFI, without RFI, excuse me. The RFI is removed is basically by eye using color augmentation. So whenever we've seen a bit of RFI, we actually removed it just by coloring the area in black. And then we actually just plotted the area, as you can see here, 0 to 20. We actually just removed that completely. So we just plotted 20 megahertz beyond that to 100. So as I said before, the 3,760 images total in each training set, and 3,760 contained the RFI seen in 0 to 20 hertz band. And then we could only manage to gather about 673 examples of the embedded RFI. So that's going beyond, that's going between essentially the 20 and 100 megahertz range. So it's actually quite small, and I'll explain later, it's actually quite not that much enough to train an algorithm like GANs. So when evaluating the network, when evaluating a GANs network, there's 2 ways we can do this. We can actually use human perception. So if you can look here, you can see here we're actually comparing on 3. So we're comparing the 2 training sets, so with RFI and without RFI, to the actual RFI organs. Just one particular note is the RFI GANs generated images is actually quite small due to computing power. We can only generate them at 256 by 256. Now, the ideal goal is to progress on this and generate much larger images. So from the visuals here, we can see that the 0 to 20 megahertz band has completely been removed from the generated set. Actually, it's made small, less intense type trees become more visible, which is quite unusual. Embedded RFI becomes partially removed. Again, this is probably due to the small training set examples of the embedded RFI training set. Struggles with small RFI bands. So you can see dotted across here, there's a small bit of RFI band kind of distorting the type trees. Again, this is probably down to the lack of examples in the embedded RFI data set. But one thing to note with human perception, this is my view, your view might be completely different. It's extremely subject to bias, so we have to put an evaluation metric on this as well. So what we use is called free shade inception distance, or FID score for short. Essentially uses the last pooling layer of the inception version 3 model prior to classification. So what we're doing is we're calculating similarities between feature vectors at the last pooling layer. And you can see from this graph here, the kind of goal is to get as close to zero as possible, indicating good similarity between data sets. So you can see here, we kind of measure here on the bottom x-axis the disturbance level of this. It's the exact same image, except we just distort it multiple times.
Jeremiah, you have 5 minutes.
Perfect. So as you can see here, as the distortion level goes up, the fit score also goes up as well. So these are the scores below. So when comparing the no RFI data set to the RFI GANs data set, we can actually indicate a score of 16. And then the no RFI data set compared to the with RFI data set, we actually get a fit score of 23.47. And this illustrates a 31.82% increase in image quality with RFI GANs. Just with future developments, as I said, I touched on before, the main kind of issue with this is the lack of examples of embedded RFI. We can only gather actually pretty prominent ones. I think it was just over 100, never mind the 673. The more prominent ones, so it's definitely quite small. So there's two ways essentially we can actually solve this. We can actually sift through the HELIOPHYSICS archive for more examples. It is quite tedious, but it would prove to be effective. But another way that we've actually tried before, when we were actually simulating type 3 and type 2 SRB data, was actually the GANs network I illustrated in slide 8. So prior to this research, we actually proven that the GANs network could actually simulate the type 3s and type 2s quite well, and quite very, very realistic. So one possible solution is kind of simulating embedded RFI. So could we increase that data set not only by augmentation, but actually by using GANs to simulate more and more embedded RFI examples? This is probably just a starting point of how to improve the network, but I'm all ears if you have any input or any questions. I'd be greatly appreciated.
Thank you. Thank you, Jeremiah. Very interesting talk. Questions? I see one on the back. Coming over.
Hey Jeremiah, it's Pierce here. It was a great talk, thanks.
Hi Pierce, how's it going?
Good. What would you say is how specific to ILOFAR is this? Could you do the same process with different radio telescopes, do you think?
Oh, absolutely. So GANs is actually very, very, it's basically, Pierce, what it does is whatever you train it on, it actually produces in a kind of a different way. We've tested on non-kind of radio astronomical stuff, and it proves quite successful at simulating data. And in terms of ILOFAR range, it's quite good at kind of simulating that type of data as well.
I have another question, if that's all right.
Yeah.
You say for the RFI below 20 megahertz, you just chop that off, is it? You don't.
For the no RFI data set, we just chopped it off. Just didn't plot, but below 20 megahertz.
And what happens if you, rather than chop it off, just color it in black, or have you tried that?
We actually haven't tried that. It's actually a good point. No, we haven't tried that at all. We're actually interested to see what would happen. Now, the only thing I'd kind of question is a possible loss in data in the type 3 maybe, but it wouldn't be too much. But it's definitely worth trying out, see what happens.
Cool, thank you.
Thanks, Pierce.
Thank you. One more question over there.
Hi, Jeremiah. It's Shane here. Just wondering
Shane.
if you could comment on any data augmentation approaches that you've looked at or tried, because obviously with only 600 and something examples, have you thought about maybe just using data augmentation to increase that?
Yeah, so we only use color augmentation, this kind of research, to get rid of the RFI, and this is purely done by eye. So it's definitely a possibility. What we could do is actually use different, as in cropping, rotations, all that sort of stuff, to increase it. But ideally what we want different forms of RFI, different positions, different sizes, just to increase that kind of diversity within the the training set. But definitely data, more data augmentation could definitely be used. Absolutely.
Right, thanks.
One more question over there.
So I was wondering what kind of data do you actually need? Because we are recently compiling a big catalog for LOFAR actually, and
Yeah.
especially we have a station that continuously observes the sun since last May. So we gathered some a fair big sample of data that we are already processing with 15 minutes chunks, so you can download just the feeds. So would that be an improvement for your?
Oh yeah, absolutely. More data, the better. We've actually used 10-minute chunks for our research, and there's plenty of data on the ILOFAR archive itself. It's just having to find essentially the right data with the right embedded RFI. Again, we could plot tens of thousands going with that RFI band between the 0 and 20 megahertz. It's just trying to find. Now, I'm not saying we could get just a load of people and just turn on the phones next to the ILOFAR station, but we just need to kind of sift through the archive itself, trying to pick out the right examples. And again, what Shane said is possibly using data augmentation and more simulation techniques just to increase that data set, because it is definitely quite small.
One question more for Andre.
Yes, thank you very much for this very interesting talk. Again, probably it's about these 673 examples. So you have here, if I understand well, you have one specific type of RFI.
Yeah,
you would actually have more than that, but probably data augmentation wouldn't really help in the sense that, if you can or not rotate them or so, you probably really need to see what are the real examples. But so what I was wondering is using other sources also of data, like other telescopes at different frequencies, like Meerkat, MWA, or these kind of things. Is that an option?
It's definitely an option. As in, we have to test it out. As in, this research is primarily built off my previous research, where we were using ILOFAR for detecting type 3 SRBs. That's the only reason why I've used this ILOFAR data. But definitely, it could be extended onto other radio telescopes as well. And it's still down to how many examples essentially we can get of that embedded RFI data, and because it is essentially the main constraint of the algorithm is having not enough examples of that.
Yeah, maybe I need to rephrase. So that means, do you think that the RFIs can be transferred from one instrument to another one? I had the impression that probably what you do with LOFAR you cannot do for another instrument, being
we probably have to see the data first. Now I don't know what other RFI looks on different radio telescopes. Probably similar enough, but we'd have to explore that option.
Thank you.
Thank you. Thanks for the question.
Thank you. Any more questions or comments? And I see nothing online, so let us thank Jeremiah again. Thank you, Jeremiah, for the interesting talk.
Thanks, everyone. Thank you.